In the depths of space and time, long before the first stars pierced the darkness, the universe existed in a state of silent anticipation. Behind the cosmic veil stretched an era astronomers call the Dark Ages, a time when the newborn cosmos was filled with neutral hydrogen that trapped all light within an opaque fog. Eventually this darkness lifted, and the faint afterglow of the Big Bang, known as the cosmic microwave background, revealed the first image of the universe, its delicate patterns of temperature variation, offering a map of everything that would one day exist. These tiny fluctuations, born from quantum tremors during the earliest fractions of a second of cosmic inflation, became the seeds from which galaxies, clusters, and vast filaments of matter grew under the guiding pull of gravity. The observable universe today extends about 46.5 billion light-years in every direction, an astonishing 93 billion light-years across in total. This size defies intuition, given that the cosmos is only about 13.8 billion years old. The paradox is resolved by understanding that space itself has been stretching over time, carrying galaxies away from one another even as their ancient light travels toward us. Imagine standing on a conveyor belt that expands while light rushes in the opposite direction. By the time those photons finally reach our telescopes, the sources that emitted them have moved unimaginably farther away. Because of this ongoing expansion, some of the galaxies we can still observe are already beyond the reach of any future signal. Light leaving them today will never arrive at Earth, as the intervening space expands faster than light can cross it. When we gaze into the deep cosmos, we are effectively looking back through time, peering across a vast ocean of distance and history that connects us to the earliest moments after creation. The cosmic microwave background acts like a snapshot of the universe's infancy, a baby picture taken 380,000 years after the Big Bang, when matter cooled enough for electrons and protons to combine into neutral atoms, allowing light to move freely for the first time. Before that instant, space was a glowing plasma that scattered photons endlessly. Opaque as the interior of a star, the release of that primordial light marked the universe's first dawn. Modern observatories, such as the Planck satellite, have charted those ancient ripples in extraordinary detail, revealing not only the universe's age and shape, but also its composition. Roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers describe a cosmos that is geometrically flat on the larger scales, an insight suggesting that space may extend without end. Beyond the faint boundary of what we can observe lies an unknowable expanse that may continue forever, filled with regions of space we will never witness because their light can never reach us. The idea is staggering. Our observable universe, for all its grandeur, may be only a small bubble within an infinite continuum. Just as a fog limits your sight to a few feet, while the landscape stretches far beyond, the cosmic horizon merely defines the limit of visibility, not of existence. Beyond it, galaxies continue to form and evolve under the same laws of physics, perhaps repeating every configuration of matter possible. In an infinite cosmos, every arrangement of atoms must occur somewhere, including exact replicas of our own world, our solar system, and even of you reading these words. This conclusion is not a flight of imagination, but a straightforward outcome of the mathematics describing an unbounded universe. Somewhere, inconceivably far away, another Earth could be orbiting a familiar sun, its inhabitants pondering the same questions. Yet infinity also guarantees uniqueness. Amid the endless repetition must exist phenomena entirely unlike anything we can conceive. Galaxies with unfamiliar physics, clusters larger than our entire visible universe, or dimensions ruled by different constants of nature. The cosmic microwave background hints at this limitless diversity, showing us only the smallest portion of the primordial fluctuations that shaped our region of space. The rest lie beyond our horizon, hidden in realms we will never reach. This realization humbles and inspires in equal measure. It reminds us that everything we can study, from the faintest galaxy to the nearest star, occupies a vanishingly small fraction of reality. Our telescopes capture but a glimmer of the vast tapestry that stretches beyond all comprehension. Still, within that narrow field of visibility resides enough wonder to fill endless lifetimes of discovery. Even if we are forever confined to this cosmic bubble, the knowledge that space continues infinitely outward transforms the way we see existence itself. The boundary of what is knowable does not define the boundary of what is real. The universe's true immensity transcends every metaphor, every number, and every human attempt to grasp it. We live inside a sphere of observation surrounded by unending mystery, a frontier that no technology, no spacecraft, no imagination can ever cross. And yet, it is precisely this unreachable horizon that gives our exploration meaning. To seek, to measure, to imagine what lies beyond the light that has finally arrived after billions of years of cosmic travel. When astronomers turned their most powerful instruments towards seemingly empty patches of the sky, what they discovered reshaped our perception of existence itself. What once appeared as darkness became a window into a sea of galaxies so distant and faint that their light had been travelling for nearly the entire age of the universe. With each improvement in telescope design, our cosmic senses has expanded, revealing not hundreds or thousands, but an estimated 2 trillion galaxies scattered throughout the observable universe. This realization redefined the boundaries of imagination. What the Hubble Space Telescope once unveiled through its deep-field images, the discovery of 10,000 galaxies in a speck of sky smaller than a grain of sand held at arm's length, has been vastly outdone by the James Webb Space Telescope. Webb's infrared vision has penetrated deeper into the ancient past, detecting light from galaxies that formed less than a few 100 million years after the Big Bang. Each of these faint smudges on the detector represents billions of stars, countless solar systems, and perhaps unnumbered worlds. The staggering implication is that our universe is far fuller, more crowded, and more intricate than anyone dared to dream only a few decades ago. The journey from Hubble to Webb mirrors the evolution of human understanding, from the first blurry glimpses of distant galaxies to a precise reconstruction of cosmic history, stretching nearly to the moment of creation. Every advance in our ability to collect light has extended the cosmic timeline we can access. Webb's instruments detect the reddened glow of galaxies whose light has been stretched by the expansion of space itself, shifting from visible wavelengths into the infrared. Observing them is like looking through a time machine, watching the universe as it was when it was less than 5% of its current age. These early galaxies often appear smaller and clumpier than modern ones, forming stars at furious rates and merging frequently as gravity sculpted the first large-scale structures. What we see in these deep fields are the building blocks of the grand spiral and elliptical galaxies that populate the universe today. Every photon that reaches Webb's mirrors carries the signature of cosmic evolution, the slow transition from simplicity to complexity, from a sea of hydrogen and helium to a universe rich with heavy elements forged in the hearts of stars. But the deep fields also reveal an even greater truth. What we can observe represents only the tiniest portion of what exists. The light from most galaxies will never reach us because they reside beyond our cosmic horizon, their photons forever lost to the accelerating expansion of space. For every galaxy we can see, countless others remain hidden in the unobservable regions of the universe, like islands receding beyond the curve of an endless ocean. This realization adds a profound humility to our pursuit of knowledge. The observable cosmos, immense as it seems, might be only a sliver of a far greater reality whose full extent is beyond even theoretical comprehension. When scientists speak of 2 trillion galaxies, they mean only within the boundaries of what light has had time to reach us. Beyond that, there may be infinite more. If space truly extends without limit, as current measurements of its geometry suggest, then the total number of galaxies is not merely large, it is infinite. Every pattern of stars, every distribution of matter, and every possible cosmic configuration exists somewhere, repeated endlessly across the boundless expanse. Our Milky Way, magnificent as it is, may be one of an infinite number of identical galaxies scattered through the infinite fabric of existence. Some of these mirror galaxies might even contain exact replicas of our solar system, right down to another version of Earth orbiting a familiar sun. The implications border on the philosophical. Infinity doesn't just allow repetition, it demands it. In an endless cosmos, every combination of atoms must occur somewhere at some unimaginable distance, endlessly replaying variations of the same cosmic theme. Yet beyond the comfort of repetition lies endless novelty. Infinity also ensures that there are phenomena entirely alien to us, galaxies governed by physics that differ subtly from our own, clusters composed of exotic matter or cosmic structures of such scale that our entire observable universe would fit within a corner of their vastness. The deeper we look, the more we realize that the universe's diversity is beyond measure. Every patch of sky, no matter how small, hides uncountable histories of birth, transformation, and decay. What began as a curiosity about faint smudges of light has evolved into a grand narrative that spans all of space and time. The hidden universe revealed by modern astronomy shows us not only where we come from, but also how little of reality we can truly grasp. It reminds us that the night sky is not an empty void punctuated by a few scattered stars, but the surface of a cosmic ocean whose depths are endless. Every glance upward is an invitation to peer further back in time, to uncover more of the story written in light, a story still unfolding, still expanding, and still far from its final chapter. Try to imagine, just for a moment, the scale of what we call the universe. It is a task the human mind was never built to handle. Numbers that once seemed vast millions, billions, trillions, lose all meaning when applied to the cosmos. If our galaxy, the Milky Way, contains roughly 400 billion stars, and if there are about 2 trillion galaxies in the observable universe, then we live in a cosmos holding around a septillion stars, that is, a 1 followed by 24 zeros. To put that in perspective, there are more stars in the observable universe than there are grains of sand on every beach and desert on Earth combined. And this, astonishingly, refers only to the region of space that light has had time to reach us from. Beyond that lies more, perhaps infinitely more, each portion of the cosmos hosting its own galaxies, its own stars, its own unknown forms of life and matter. The scale is not simply large, it is conceptually infinite, transcending comprehension. When astronomers count stars, they are not counting points of light so much as histories. Each star a story of birth from collapsing gas, of fusion's luminous struggle against gravity, and of eventual death in silence or explosion. Stars are the true engines of cosmic evolution. From the hydrogen that dominates the early universe, they forge the heavier elements, carbon, oxygen, iron, and beyond. Every atom of calcium in your bones, every molecule of oxygen you breathe, every trace of iron in your blood, all of it was made inside a star. In a real and literal sense, we are made of the universe's memory. The light we see from distant galaxies carries the record of these stellar lives, travelling for billions of years to reach our eyes. When we gaze into the night sky, we are looking not just into space, but through time. The light from the nearest star takes over 4 years to reach us. From the farthest galaxies, more than 13 billion. Some of those galaxies no longer even exist in their original form. The light that left them when the first multicellular life was forming on Earth is only now arriving at our telescopes. It is as if the universe itself is performing a slow, magnificent act of self-revelation, unveiling its story frame by frame over cosmic time. The numbers that describe this reality strain language to breaking. Astronomers use scientific notation as a way of coping with the unimaginable. But the human heart doesn't think in exponents, it feels in images. So imagine this. If each star were represented by a single grain of sand, then all the stars of the Milky Way would fill a stretch of beach 2 miles long and 100 feet wide. To represent every star in the observable universe, that beach would have to wrap completely around Earth, dozens of times over. Each of those grains could host worlds, and on some of those worlds, perhaps, creatures may look upward and wonder as we do now. The act of counting stars is really an act of counting possibilities. Around most stars orbit planets, and many of those planets lie within habitable zones where liquid water could exist. Statistically, there may be more habitable worlds than stars themselves, since multi-planet systems are the rule rather than the exception. The odds of life appearing somewhere else in this grand expanse approach certainty. Yet despite these astronomical probabilities, the silence of the sky remains unbroken. We listen for signals, watch for anomalies, and still find none. Perhaps the distances are simply too vast. Perhaps civilizations rise and fall long before their light or radio waves can reach us. Or perhaps, in a universe so immense, life is common but communication is impossible. Each world an island separated by cosmic seas that cannot be crossed. Even so, the sheer quantity of stars ensures that every conceivable variation of existence is being played out somewhere. There may be worlds where life thrives under crimson suns, worlds ruled by frozen methane oceans, and worlds lit by twin stars casting overlapping shadows across alien continents. The arithmetic of the cosmos tells us that the extraordinary must occur not once, but endlessly. Counting the stars, then, is not a sterile mathematical exercise. It is a meditation on infinity, a reflection on creation's boundless imagination. The next time you step outside and look into the night sky, know that you are witnessing only a fraction of what truly exists. Every point of light is a sun, every sun perhaps a system, every system a potential cradle for consciousness. The numbers may overwhelm us, but they also elevate us. To count the stars is to recognize that we are part of something immeasurably vast and beautifully intricate, a cosmic ocean whose depths we have only begun to explore. It is a reminder that while our planet is small and our lives brief, the matter composing us has journeyed through that ocean for billions of years, passing through the hearts of stars carried by the winds of supernova, scattered into space, and reassembled into life capable of counting, thinking, and dreaming about the stars that made it possible. Our home galaxy, the Milky Way, drifts through the vastness of space as part of a small but intricate community of galaxies known as the Local Group. This cluster of more than 60 members, bound together by the invisible hand of gravity, occupies a region about 10 million light-years across. At its heart are two colossal spirals, the Milky Way and the Andromeda Galaxy, each containing hundreds of billions of stars, accompanied by a retinue of smaller dwarf galaxies that orbit them like celestial satellites. The Triangulum Galaxy, slightly smaller but still significant, rounds out this trio of dominant players in our cosmic neighborhood. When viewed from afar, the Local Group would appear as a delicate cluster of shimmering islands floating in an endless sea of darkness, their faint halos of stars and gas weaving together into a gravitational ballet that has been unfolding for billions of years. The Milky Way itself is a vast spiral of rotating stars, gas, and dark matter, stretching over 100,000 light-years from end to end. Its disk contains winding arms rich with star-forming regions, while a dense bulge of older stars marks its center, where a supermassive black hole known as Sagittarius A resides. Around this central region, the entire galaxy spins like an enormous cosmic wheel, with our solar system located about 27,000 light-years from the core. From our vantage point inside one of its spiral arms, we can only glimpse fragments of its structure, like sailors aboard a ship who can never see the full outline of the ocean they cross. Surrounding this great disk is a faint halo of dark matter, invisible but crucial. It holds the galaxy together, ensuring that its outer stars do not simply drift away into the void. Nearby, Andromeda mirrors our own structure on an even grander scale. It is slightly more massive and extends nearly 200,000 light-years across. Its spiral arms gleam with blue-white light from billions of young stars, while its center glows faintly golden, illuminated by an ancient population of suns that have burned for more than 10 billion years. Like us, Andromeda is encircled by smaller companions dwarf galaxies that bear silent witness to eons of gravitational interaction. Between these two giants, invisible threads of gravity are already drawing them together. In about 4 billion years, the Milky Way and Andromeda will collide in a slow, majestic merger that will reshape both galaxies into a single, massive elliptical system. Long before that cosmic encounter, however, smaller interactions continue to shape our surroundings. The Milky Way is already devouring several of its own satellites, pulling apart galaxies such as the Sagittarius Dwarf and the Canis Major Dwarf, their stars stretched into glowing streams that wrap around our galaxy like faint ribbons. These mergers are not acts of destruction, but of renewal. Each infusion of stars and gas adds new material to the Milky Way, helping to form new generations of suns and planets. On an even larger scale, our Local Group itself is just one filament within a colossal web of galaxies stretching across hundreds of millions of light-years. The group is part of a vast gravitational basin known as the Virgo supercluster, which in turn belongs to an even larger structure called Laniakea, a name meaning immense heaven in Hawaiian. This sprawling supercluster spans over 500 million light-years and contains roughly 100,000 galaxies, all connected by subtle gravitational flows that pull them toward a mysterious region known as the Great Attractor. Within this immense structure, The Milky Way and its neighbours drift along invisible currents shaped by the combined mass of countless galaxies and the dark matter between them. The motion is imperceptible on human timescales, yet over cosmic epochs it carries entire galaxies across the universe like leaves on an intergalactic river. When we trace these movements backward, they lead us to a common origin, a denser, younger universe where the first proto-galaxies began to form. When we project them forward, they hint at a far future when gravity will merge clusters and superclusters into even larger cosmic structures before dark energy eventually drives everything apart. To understand our place in this grand hierarchy is to grasp both our insignificance and our connection to the vast totality of existence. Earth is not merely a planet orbiting a star. It is a grain of dust embedded within the spiral arm of a single galaxy, itself one of trillions forming a cosmic web that stretches beyond imagination. The night sky we see from our backyards is a tiny window into this immense architecture. Each point of light, each faint smear of brightness through a telescope is a member of this cosmic neighbourhood, a silent companion in our journey through an expanding universe. And though the distances separating these galaxies are measured in millions of light-years, gravity binds them into a single dynamic system whose story is still unfolding. Beyond the borders of our local group, the cosmic architecture expands into structures so vast that even the imagination strains to hold them. Galaxies are not scattered randomly through the universe, but gather into sprawling clusters and superclusters, each linked by filaments of dark matter and gas that form the framework of the cosmic web. These filaments stretch for hundreds of millions of light-years, weaving an invisible lattice that dictates where galaxies form and how they move. Between them lie immense cosmic voids, enormous regions nearly empty of galaxies, like bubbles in an intergalactic foam. Together, this network of filaments and voids defines the large-scale structure of the universe. Our local group itself is just one small knot in this cosmic web, located on the outskirts of a colossal supercluster called Laniakea. This immense region, whose name in Hawaiian means immense heaven, spans roughly 500 million light-years and contains about 100,000 galaxies. Within its boundaries flow rivers of galaxies drawn inward by the combined pull of gravity, all drifting toward a mysterious gravitational center known as the Great Attractor. To visualize this structure, imagine space not as a void but as a dynamic ocean of matter, where entire galaxies are like plankton carried by the slow, relentless currents of cosmic gravity. Astronomers map these motions using redshift surveys, which measure how light from distant galaxies is stretched by cosmic expansion. These observations reveal not chaos but pattern, a grand choreography in which galaxies trace the underlying shape of dark matter, the invisible substance making up most of the universe's mass. Gravity, acting over billions of years, has sculpted these filaments and nodes from the primordial fluctuations seeded during the universe's earliest moments. In the beginning, matter was distributed almost perfectly evenly, yet tiny quantum ripples in the density of the early universe grew over time into the enormous structures we see today. Where the density was slightly higher, gravity gathered gas and dark matter, eventually forming galaxies and clusters. Where it was lower, space expanded faster, creating the great cosmic voids. What we observe today is the frozen record of that ancient process, an intricate network of luminous matter tracing the outlines of something far vaster and unseen. The scale of these structures is staggering beyond comprehension. The Virgo cluster, our nearest large cluster, contains several thousand galaxies within a sphere 15 million light-years across. Farther out, superclusters like Hydra Centaurus and Shapley form gravitational behemoths that each contain tens of thousands of galaxies. And yet even these colossal formations are only local features within an even grander structure. The observable universe itself filled with countless other superclusters, arranged into a filamentary pattern stretching in every direction. The cosmic web is, in effect, the skeleton of the universe. Through gravitational lensing, where the mass of invisible dark matter bends the light from distant galaxies, astronomers have been able to trace this skeleton's contours. The images that result show that galaxies lie along filaments like beads on invisible strings, their clusters shining at the intersections where filaments meet. Between these glowing strands lie the great cosmic voids, regions tens or even hundreds of millions of light-years wide where matter is scarce and galaxies are few. These voids are not truly empty, however. They contain thin, diffuse gas and dark matter, silent witnesses to the universe's ongoing expansion. The discovery of this vast interconnected web has transformed cosmology. For centuries, people imagined the universe as a simple collection of stars scattered through space. We now know it is a structured organism, with galaxies functioning like cells in a living body, connected by filaments of gravity and cosmic gas. Each cluster, each filament, contributes to the whole. On the larger scales, the universe displays a kind of order that echoes biological or geological forms, as though the same principles of pattern and connection operate across all levels of reality. And still, our instruments can see only so far. Beyond the limits of our observation, the web continues, possibly without end, repeating its intricate geometry on scales we cannot yet fathom. The existence of such order across distances measured in hundreds of millions of light-years invites philosophical wonder as much as scientific curiosity. It suggests that our universe is not a chaotic void, but a coherent whole, shaped by fundamental forces acting with quiet precision over cosmic time. From our small position within the Milky Way, we can trace the contours of this structure and understand our place within it, but we cannot yet glimpse its ultimate boundaries. Laniakea, magnificent though it is, may itself be just one region of a much larger and more complex structure, a single wave within an infinite cosmic ocean. The patterns we observe may repeat endlessly, hinting at a reality grander than any map we could draw. Every galaxy, every cluster, every supercluster forms a verse in this cosmic poem written across space and time, a reminder that even the vastest structures in existence are part of something larger still, beyond the reach of our instruments, but not beyond the reach of human wonder. Galaxies, magnificent as they appear from afar, are not the tranquil islands of light they seem. Beneath their elegant spirals and glowing halos lies a history of violence, a record of collisions, mergers and devourings that has shaped the universe over billions of years. The Milky Way itself is no exception. Far from being a solitary wanderer, it is a cosmic predator, slowly consuming smaller companions that stray too close to its gravitational grasp. Around our galaxy, faint streams of stars arc across the sky remnants of dwarf galaxies torn apart by tidal forces. The Sagittarius dwarf spheroidal galaxy, once an independent system, has been shredded into a ribbon of stars that now wraps around the Milky Way's halo. Another victim, the Canis Major dwarf galaxy, is being stretched and dispersed, its stellar population gradually assimilated into our own. These stellar streams form ghostly bridges between galaxies, the lingering evidence of ancient feasts that have continued since the Milky Way's youth. Astronomers call this process galactic cannibalism, and though the term evokes brutality, it is through such mergers that galaxies grow. A large spiral like ours is built from countless smaller ancestors, each swallowed whole and digested into its structure. When a dwarf galaxy approaches, gravity begins its slow work, stripping away stars and gas, reshaping orbits, and distorting both systems. Over hundreds of millions of years, the smaller galaxy dissolves completely, its material scattered among the Milky Way's stars, thickening the disk and enriching it with new elements. What may seem destructive on the scale of a single galaxy is, on the scale of the cosmos, an act of creation, an ongoing cycle through which galaxies evolve from simple clouds of gas into the complex systems we observe today. The large and small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, are next in line to face this cosmic fate. They are bound to the Milky Way by gravity, orbiting like twin satellites on elliptical paths that bring them gradually closer. Over time, the gravitational pull of our galaxy distorts their shapes, drawing out long trails of hydrogen gas that stretch for hundreds of thousands of light-years, known collectively as the Magellanic Stream. This enormous arc is a sign of their slow unravelling, a prelude to their eventual absorption. As the clouds spiral inward, their gas will collide with the Milky Way's outer halo, triggering bursts of new star formation across our galaxy's edge. These future stellar nurseries will light up the sky, marking the next phase in the Milky Way's evolution. Such encounters are common throughout the universe, In galaxy clusters, interactions are frequent and fierce. Smaller galaxies fall prey to larger ones, their stars stripped and scattered, their identities erased. In some cases, these mergers are spectacularly visible, with distorted arms, tidal tails, and luminous bridges stretching between galaxies. Observatories like Hubble and Webb have captured hundreds of such systems mid-collision, frozen in various stages of their transformation. What these images reveal is that galaxies are dynamic organisms, not static collections of stars. They are constantly reshaped by gravity's relentless tug-of-war. Even within our own galaxy, we can still detect the signatures of past conquests. Streams of ancient stars move in coherent paths through the halo, tracing the ghosts of long-vanished galaxies. By mapping their motion and composition, astronomers can reconstruct the Milky Way's history of mergers, piecing together a fossil record of cosmic evolution. The data show that our galaxy has grown substantially over time, its mass increasing through the steady consumption of smaller systems. Without this ongoing process, it would be far less massive, its spiral arms less prominent, its halo thinner and dimmer. Galactic cannibalism is not merely a quirk of cosmic behavior, it is the engine of growth for most galaxies in the universe. Even giant ellipticals, the smooth, featureless galaxies found in dense clusters, owe their size and brightness to a long history of mergers that blended many smaller progenitors into one. And yet, this process continues today. In the near future, cosmically speaking, the Milky Way will meet its greatest rival, the Andromeda Galaxy. The two are currently separated by about 2.5 million light-years, but they are hurtling toward each other at a speed of roughly 110 kilometers per second. 4 billion years from now, their halos will touch, their disks will interpenetrate, and a slow, magnificent collision will begin. For the next few billion years, stars will be scattered and reformed, vast plumes of gas will ignite in waves of new star birth, and the familiar spiral patterns of both galaxies will dissolve. When the cosmic dust settles, the Milky Way and Andromeda will have merged into a single, enormous elliptical galaxy, Milkomeda, as some astronomers call it. Our solar system will survive the collision, likely carried into a wide new orbit around the merged galaxy's core. From whatever planet intelligent beings may observe the event, the night sky will blaze with the combined light of two galaxies in union, a spectacle of unimaginable beauty born from destruction. This, then, is the destiny written into the fabric of galactic evolution. Growth through collision, creation through chaos, life born from the ruins of what came before. Among the Milky Way's companions, the large and small Magellanic Clouds stand as two of the most striking and dynamic features in our galactic neighbourhood. Visible to the unaided eye from the southern hemisphere, these irregular dwarf galaxies drift through the night like pale, ethereal smudges. For centuries they puzzled observers, appearing almost ghost-like against the southern sky. But modern astronomy has revealed them to be living remnants of a long cosmic story, a story of motion, interaction, and inevitable destiny. The Magellanic Clouds are bound to the Milky Way by gravity, engaged in a slow and intricate dance that will ultimately end in their absorption. Each orbit brings them closer, their paths drawn inward by the vast gravitational pull of our galaxy's dark matter halo. The Large Magellanic Cloud, or LMC, lies roughly 160,000 light-years away and spans about 14,000 light-years in diameter, while the smaller SMC trails slightly farther, about 200,000 light-years distant. Together they contain billions of stars, enormous clouds of hydrogen gas, and some of the most active regions of star formation in the local universe. Their irregular shapes are not accidental but sculpted by tidal forces as they interact with one another and with the Milky Way's outer halo. The gravitational tug between them has produced long, ghostly trails of gas that extend like filaments across intergalactic space. These are the Magellanic Stream, and the leading arm vast rivers of hydrogen stretching over 500,000 light-years, wrapping around the Milky Way like delicate threads of cosmic silk. The stream itself is a testament to the power of gravity's slow persistence. Over billions of years, the Milky Way's pull has stripped gas from the clouds, creating this immense ribbon that glows faintly in radio wavelengths. Within the clouds, star formation burns brightly. The LMC's Tarantula Nebula is among the most vigorous stellar nurseries known, a maelstrom of gas and dust where massive stars are born in clusters, their ultraviolet radiation carving cavities in the surrounding material. These newborn giants live fast and die young, exploding as supernovae that enrich their environment with heavy elements, seeding future generations of stars and planets. The entire region is a miniature laboratory for understanding how galaxies evolve. Astronomers can observe in real time the processes that, on larger scales, shaped galaxies throughout cosmic history. The interplay of gas inflow and outflow, the ignition of new stars, and the feedback from supernovae that stirs and sculpts the surrounding medium. Yet even as the Magellanic Clouds blaze with life, their fate is sealed. Computer simulations suggest that within a few billion years, both will spiral inward and merge completely with the Milky Way. Their stars will disperse into our galaxy's outer disk and halo, their gas absorbed to fuel new rounds of star formation. The collisions and tidal disruptions that precede this final merger will ignite spectacular waves of stellar birth, temporarily transforming parts of the Milky Way into starburst regions glowing with thousands of newborn suns. The gravitational disturbance may even awaken the supermassive black hole at the center of our galaxy, triggering an outburst of energetic radiation as it accretes new material. The Milky Way will grow in both size and brightness, reshaped once again by the same cosmic process that has governed galactic evolution since the beginning. Though their disappearance will mark the end of the Magellanic Clouds as separate entities, their substance will live on, redistributed across our galaxy. The stars, now shining in their delicate arms, will become part of the Milky Way's great stellar population, their atoms eventually recycled into new generations of stars and planets. The gas they contribute will enrich our galactic ecosystem, ensuring that the cycle of creation continues. The Magellanic Clouds are, in essence, cosmic bridges between the past and the future, a glimpse of how galaxies grow and sustain themselves through continual renewal. Their story also illustrates the delicate balance between destruction and creation that defines the universe. The gravitational tides that tear them apart are the same forces that spark the birth of new stars. The collisions that distort their structure are the very events that keep the cosmos alive with change. In the grand symphony of the universe, nothing remains still and nothing is wasted. Every galaxy, large or small, plays its part in the endless process of transformation. When future observers look up at the sky billions of years from now, the Magellanic Clouds will be gone, their light dispersed across the Milky Way's halo. But their legacy will endure in the brilliance of the stars they helped to create and in the quiet, ongoing rhythm of the galaxy that absorbed them. Through them we are reminded that even in the vast, impersonal machinery of the cosmos, there is continuity, a kind of cosmic immortality in which everything that falls becomes part of something greater, shining anew in the endless night. Far beyond the serene glow of the Milky Way's spiral arms, another vast island of stars approaches us in silence. The Andromeda Galaxy, our closest galactic neighbour, is on a slow but inevitable collision course with our own. It lies about 2.5 million light-years away, yet in cosmic terms, that distance is practically next door. When ancient astronomers first observed Andromeda as a faint, misty patch of light in the night sky, they could not have imagined that it was an entire galaxy of 1 trillion stars, larger than our own, and hurtling toward us at more than 100 kilometers per second. For billions of years, gravity has been drawing the Milky Way and Andromeda together, and their fates are now intertwined. This future merger will not be a sudden or violent crash, but a slow cosmic ballet unfolding over billions of years. The vast emptiness between stars means that direct stellar collisions will be extremely rare. Instead, the drama will play out through gravity's subtle choreography. As the two galaxies approach, their immense halos of dark matter will interact first, tugging at one another and distorting their shapes. Then their outer arms will begin to interpenetrate, flinging long tidal tails of stars into intergalactic space. The sky from Earth, or whatever worlds survive within the merging galaxies, will transform into a spectacle beyond imagination. At first, Andromeda will appear as a small brightening smudge, growing larger each night as millennia pass. When the galaxies finally begin to overlap, the heavens will blaze with streams of stars stretching across the sky, like luminous rivers of fire suspended in darkness. The familiar constellations will dissolve, replaced by an ever-shifting mosaic of light. For a time, the combined gravitational forces will compress clouds of gas, triggering a wave of star formation so intense that it will rival the brightness of quasars. Entire regions of both galaxies will ignite in bursts of stellar creation, their new stars shining fiercely blue before dying in supernovae that enrich the surrounding space with heavy elements. Astronomers have modelled this grand encounter in exquisite detail using powerful computer simulations. The two galaxies will make several close passes over the course of a few billion years, each encounter distorting their disks further and flinging out arcs of material that stretch for hundreds of thousands of light years. Eventually, friction and gravitational drag will cause their orbits to decay until they merge completely into a single, massive elliptical galaxy. This new cosmic city of stars has been given the informal name Milkomeda, a union of Milky Way and Andromeda. It will be a golden, rounded system, lacking the graceful spiral arms that once defined its parents, but shining with the blended light of nearly 2 trillion stars. The night sky, as seen from a surviving planet, will never be dark again. It will glow with a perpetual soft radiance from millions of nearby suns. Despite the enormity of this event, our solar system itself will likely survive relatively unscathed. The distances between stars are so immense that even during the merger, the odds of 2 stars colliding are infinitesimally small. However, the Sun's orbit will be thrown into chaos by the shifting gravitational landscape. Simulations suggest that our solar system could be flung farther out from the galactic centre, possibly into the extended halo of the new galaxy, where the night sky would appear thinner but filled with strange, unfamiliar constellations. If humanity or its descendants still exist to witness the merger, they will behold one of the greatest spectacles in the history of the cosmos. 2 galaxies slowly becoming one, their stars intermingling in a luminous embrace that spans hundreds of thousands of light years. The Andromeda collision also carries deeper implications for our understanding of cosmic evolution. It reminds us that galaxies are not static structures, but ever-changing entities shaped by gravity's endless cycle of attraction and merger. Every large galaxy we see today, including the Milky Way and Andromeda themselves, was forged through countless such encounters. Smaller galaxies merge to form larger ones, which then merge again, gradually building the universe's grand architecture over billions of years. The upcoming union of the Milky Way and Andromeda is simply the next chapter in that ongoing story, a continuation of the process that began shortly after the first galaxies formed. Once the merger is complete, Milkomeda will likely become part of a growing cluster as it attracts other nearby galaxies from the local group, such as the Triangulum galaxy and various dwarfs. Over hundreds of billions of years, these systems will coalesce into a single, enormous elliptical galaxy, glowing dimly as its stars age and fade. Eventually, the accelerating expansion of the universe will carry all other galaxies beyond our cosmic horizon, leaving the descendants of Milkomeda isolated in an ever-darkening void. Yet even in that far future, the legacy of the Milky Way and Andromeda will live on in the merged galaxies' stars, planets, and nebulae, a testament to the universe's ceaseless creativity through destruction. The collision is not an end but a transformation, an act of cosmic renewal on a scale that defies human comprehension. It is a reminder that change is the universe's only constant, and that even the grandest structures are subject to the same eternal rhythm of birth, decay, and rebirth that governs all things, from the life of stars to the destiny of galaxies themselves. Among the billions of galaxies scattered across the universe, most follow predictable patterns that align with our understanding of cosmic evolution. They grow by accreting gas, merging with smaller companions, and forming new generations of stars over billions of years. Yet, scattered among them are rare anomalies, galaxies that defy the rules, that seem far too massive, too ancient, or too dead for their place in cosmic history. These mysterious systems, sometimes called red and dead galaxies, appear to have stopped forming stars almost as soon as they began. One of the most striking examples is a galaxy known as Max Twymenrun 29-1, a massive, compact system observed as it existed roughly 10 billion years ago. According to everything we know about the timeline of cosmic evolution, a galaxy that large and quiescent should not have existed at such an early epoch. It formed its stars rapidly, consumed its gas supply, and then abruptly went dark, its light fading into a deep crimson hue as its stellar population aged. To astronomers, it is as though the universe skipped ahead several billion years in its script. These early dead galaxies challenge our models of how matter condenses, how gas cools, and how star formation proceeds. Theorists have long assumed that galaxies at that stage of the universe, just a few billion years after the Big Bang, should still be turbulent star factories, their disks bursting with activity. Yet here is evidence of galaxies that had already lived fast and died young, suggesting a cosmic efficiency we do not yet fully comprehend. How could such galaxies quench their star formation so completely and so early? One explanation points to supermassive black holes lurking at their centres. When these giants feed on surrounding gas, they unleash torrents of energy in the form of jets and radiation, powerful enough to blow away or heat the galaxy's remaining gas, effectively shutting down the formation of new stars. This process, known as feedback, acts as a kind of galactic self-regulation. The same force that drives growth eventually enforces stillness. Another possibility is environmental. The galaxies may have formed in regions of space where the surrounding intergalactic medium was stripped away or heated by early quasars, cutting off the supply of fresh material needed to sustain starbirth. Whatever the mechanism, these galaxies are fossils of an accelerated evolution, clues to an era when the universe's first great structures were taking shape. The James Webb Space Telescope has deepened this mystery. Its infrared eyes have revealed even more examples of massive galaxies forming astonishingly early, some less than 500 million years after the Big Bang. These primordial giants are far too mature for their age, containing billions of stars in a universe that should still have been assembling its first building blocks. Their existence implies that galaxy formation began faster and more efficiently than our models predict, perhaps driven by dense pockets of dark matter that collected gas at unprecedented rates. Webb's discoveries have forced cosmologists to reconsider long-held assumptions about how quickly complexity can arise from the primordial chaos. Each of these unexpected galaxies stands as a quiet rebellion against our theories, a reminder that the universe is under no obligation to behave according to our expectations. The mystery of early death is equally profound. Some of these galaxies, after their initial starburst phase, seem to have gone completely dormant, not just slowing but halting star formation altogether. In them, the brilliant blue glow of young stars has faded, replaced by the steady red shimmer of aging suns. Their energy output declines, their spiral arms blur, and their once vibrant gas disks settle into silence. Yet even in their quiescence, they remain beautiful cosmic embers glowing softly against the dark. They tell a story of both creation and exhaustion, of forces that push the universe toward order and stasis after periods of furious transformation. Understanding these impossible galaxies is one of the great challenges of modern astronomy. They force us to confront the limits of our models and the complexity of the processes that shape the cosmos. Perhaps the universe is simply more efficient than we thought, capable of building large systems almost immediately after its birth. Or perhaps our understanding of physics at those early times is incomplete, requiring new insights into the behavior of dark matter, gas cooling, and the feedback effects of early black holes. Whatever the answer, these galaxies that shouldn't exist expand our sense of wonder. They are the universe's quiet reminders that there is still much we do not know, that even after mapping billions of light-years of space, mysteries remain woven into the very fabric of cosmic time. In their defiance of expectation, they embody the essence of discovery itself. The more we uncover, the more the universe humbles us, revealing that its story is far richer and stranger than our equations can yet describe. The red and dead galaxies are not errors in nature, but evidence of a cosmos still whispering secrets we have only begun to hear. In the immense theatres of galaxy clusters, where thousands of galaxies move through a sea of scorching plasma, an extraordinary and haunting class of objects drifts among them, galaxies that trail luminous tendrils of gas and stars like cosmic jellyfish. These so-called jellyfish galaxies are both beautiful and tragic, their graceful forms born from violent encounters with the hostile environments in which they reside. When a galaxy plunges into the dense hot gas that fills a massive cluster, it experiences a force known as ram pressure stripping. This invisible wind, created by the galaxy's motion through the intergalactic medium, can be strong enough to tear away its gas, the raw material for star formation, leaving behind long, streaming filaments that shine in the ultraviolet and visible light of newly formed stars. In a single moment of cosmic time, a spiral galaxy can be transformed into something otherworldly, a glowing, translucent organism drifting through space, its bright core trailed by delicate ribbons of stellar light. One of the most striking examples of this process is the galaxy ESO 137001, located in the Norma cluster about 200 million light-years from Earth. As it hurtles through the dense core of the cluster at nearly 2 million kilometers per hour, the galaxy sheds vast quantities of gas, creating two glowing tails that stretch for more than 200,000 light-years. These tails are filled with young, hot stars born from the very material being stripped away. Seen through telescopes like Hubble and Chandra, ESO 137001 appears almost alive, a bright compact head with twin luminous tentacles streaming behind it, glowing in X-rays and hydrogen emission. It is a vision both of destruction and of creation, a reminder that even in the most violent corners of the cosmos, new life emerges from chaos. Ram pressure stripping is one of the key mechanisms by which galaxies evolve within clusters. As galaxies fall into these enormous gravitational wells, they are subjected not only to the tidal forces of their neighbours, but also to the pressure of the intracluster medium, a thin but extremely hot gas that can reach tens of millions of degrees. This gas is nearly invisible to optical telescopes, but glows brightly in X-rays, forming an ocean of plasma in which galaxies are mere swimmers. When they move through it at high speeds, the pressure acts like a cosmic hurricane, blowing away their interstellar medium. Without gas, a galaxy can no longer form new stars, and over time it fades, transforming from a blue star-forming spiral into a dull, red elliptical. The jellyfish phase is thus a fleeting moment, a transitional state between life and death on a galactic scale. Yet, paradoxically, the stripping process can ignite new waves of star formation in the very material being expelled. As the gas is compressed by ram pressure, it collapses into knots that give birth to clusters of young stars, creating glowing trails that stretch for hundreds of thousands of light-years. Some of these stars remain bound to the parent galaxy, while others drift away, forming diffuse stellar streams that may one day populate the intracluster space. In this way, jellyfish galaxies contribute not only to their own demise but also to the enrichment of the larger cosmic environment. Their expelled material seeds the space between galaxies with metals and energy, helping to shape the evolution of entire clusters. They are, in a sense, cosmic pollinators, spreading the elements of life through intergalactic space. The discovery and study of jellyfish galaxies have provided astronomers with a new perspective on how environment influences cosmic evolution. They show that galaxies are not isolated systems, but participants in a vast ecological network, constantly exchanging matter and energy with their surroundings. The violent forces that act upon them, gravity, pressure, radiation, are the same forces that govern the growth of structure throughout the universe. In recent years, high-resolution observations from telescopes like the Very Large Telescope and the James Webb Space Telescope have revealed intricate details of these galaxies' anatomy. Turbulent shock fronts, regions of ionized gas, and filaments that shimmer with newborn stars. Each observation tells a story of struggle and transformation. Over time, the stripped galaxy will settle into quietude, its reservoirs of gas exhausted, its once spiral arms erased, leaving behind a spheroidal remnant drifting through the cluster's core. But its luminous trails will persist for millions of years, silent witnesses to its final act of creation. To look at a jellyfish galaxy is to glimpse the universe's paradoxical artistry. Out of violence comes beauty, out of destruction, renewal. These cosmic apparitions, suspended between being and dissolution, remind us that the universe's creativity knows no gentleness. It reshapes and reuses everything, turning loss into light. In their radiant decay, the jellyfish galaxies embody the dual nature of the cosmos, indifferent yet magnificent, brutal yet breathtaking, forever destroying and creating in the same eternal motion. In the grand architecture of the cosmos, galaxies are not only collections of stars but also structures held together by invisible frameworks. This scaffolding made of dark matter forms the skeleton upon which the luminous matter of stars and gas is arranged. Without it, galaxies as we know them could not exist. Their disks would spin apart, their stars would drift away into the void. Yet in recent years, astronomers have discovered a handful of galaxies that appear to break this fundamental rule: enigmatic systems that seem to have little or no dark matter at all. The most famous among them is NGC 1277, a compact lenticular galaxy located about 240 million light-years away in the Perseus cluster. When scientists measured its rotation curve and mass distribution, they found something astonishing. The stars themselves accounted for nearly all of its gravitational pull. If the data are correct, this galaxy contains barely 1% of the dark matter that theory predicts should be present. It is, in essence, a galaxy without a skeleton. NGC 1277 is an ancient system, composed mostly of old, metal-rich stars that formed more than 10 billion years ago. It has not made new stars since that time, suggesting that it is a relic from the early universe, a fossil galaxy preserved almost unchanged for eons. Unlike most galaxies of its size, it lacks a significant halo of gas and dust. Its stars are packed tightly together in a dense golden core that rotates rapidly, like a stellar whirlpool frozen in time. This compactness may hold the key to its strange nature. Some astronomers propose that during its youth, NGC 1277 was part of a larger, dark, matter-rich halo, but was later stripped of its outer layers by gravitational interactions with neighbouring galaxies in the cluster. Over time, these encounters may have peeled away its dark matter and gas, leaving behind only the luminous core we see today. Others argue that it may have formed in an unusually dense region of space where baryonic matter dominated from the start, a rare exception to the cosmic norm. Whatever its origin, the discovery of galaxies like NGC 1277 poses a profound challenge to our understanding of cosmology. The existence of even one such object calls into question the universality of dark matter's role in galaxy formation. For decades, the LCDM model, our standard description of the universe, has rested on the assumption that every galaxy is embedded within a massive halo of dark matter. This unseen material, which interacts only through gravity, provides the necessary glue to explain the motions of stars and the growth of cosmic structure. If galaxies can exist without it, we may be missing something fundamental about the way gravity works on large scales. Some physicists have suggested that such anomalies could point to modifications in our theory of gravity itself, invoking alternatives such as modified Newtonian dynamics, MOND, which posits that the force of gravity behaves differently in regions of extremely low acceleration. In this view, galaxies like NGC 1277 are not exceptions, but hints that our equations may need refinement. Yet even within the standard model, nature finds ways to surprise us. Observations have since uncovered other galaxies with similarly puzzling properties, including the ultra-diffuse galaxies NGC 1052 DF2 and NGC 1052 DF4. These ghostly systems, located about 60 million light-years away, are so faint that they were nearly invisible until powerful telescopes revealed their true extent. They are enormous, comparable in size to the Milky Way, but contain only a fraction of its stars. When astronomers measured the motion of star clusters within them, they found that the speeds were far too low to require the usual amount of dark matter. Like NGC 1277, these galaxies seem almost weightless, defying expectations. And yet, paradoxically, others in the same region show an overabundance of dark matter, as though the cosmic ledger had been balanced elsewhere. The implications are staggering. It may be that dark matter can be displaced or redistributed during galaxy interactions, creating regions of scarcity and excess. Or perhaps these galaxies formed under rare conditions that temporarily suppressed the influence of dark matter, leaving us to observe them in a fleeting and unusual state. As observations grow more precise, we continue to uncover nuances that complicate the tidy picture of galactic physics. Each discovery forces us to confront how little we truly understand about the unseen forces shaping the cosmos. The so-called galaxies without skeletons are not just scientific curiosities, they are cracks in our theoretical foundation, glimpses of a deeper reality waiting to be uncovered. Whether they represent exotic interactions, measurement errors, or signs of new physics, they remind us that even in a universe governed by invisible matter, there are places where light stands on its own. In NGC 1277's dense golden core, the stars spin freely, seemingly unmoored from the dark framework that defines almost every other galaxy. It is a strange, elegant survivor, a relic from a different era of cosmic evolution, whispering that the universe still holds secrets beyond the reach of our most trusted models. In the dawn of time, when the universe was still young and unformed, vast cosmic structures began to take shape out of the cooling chaos of primordial gas. For decades, astronomers believed that the early cosmos was a place of small, fragile galaxies, tiny turbulent systems just beginning their long process of growth. But recent observations, particularly from the James Webb Space Telescope, have shattered that expectation. Instead of finding only infant galaxies, Webb has uncovered enormous mature systems, already glowing red with old stars less than 1 billion years after the Big Bang. These massive entities, dubbed the red monsters of the early cosmos, should not exist according to our standard models of galaxy formation. They appear too evolved, too massive, and too quiescent for such an early epoch, as though time itself had somehow run faster for them. Their reddish hue is not the result of dust or distance alone, but of age. Red light means that their stars are old and cool, indicating that these galaxies experienced a brief but intense burst of star formation early on, followed by a rapid shutdown. Some of them already contain as many stars as the Milky Way, packed into regions far smaller. They are compact, heavy, and eerily calm cosmic elders living in a universe that should still have been in its infancy. The discovery of these ancient giants has forced scientists to rethink the timeline of cosmic evolution. The prevailing theory once held that galaxies gradually built up their mass through mergers and accretion over billions of years. Yet these red monsters suggest that some galaxies achieved maturity almost immediately, assembling their stars in frantic bursts lasting only a few 100 million years. To do so, they must have converted gas into stars with extraordinary efficiency, perhaps 10 times faster than galaxies do today. But such rapid growth comes at a cost. The very processes that drive star formation also produce winds, radiation, and supernova explosions that can blow away or heat the remaining gas, effectively quenching further activity. This self-limiting behavior may explain why these galaxies burned brightly and then went silent, becoming the red, dormant systems we now observe. Their existence raises profound questions about the universe's earliest epochs. How could so much matter coalesce so quickly? One possibility lies in the dark scaffolding of the cosmos. Perhaps these galaxies formed within unusually massive dark matter, halos dense regions where gravity gathered matter with great speed, allowing gas to cool and collapse more rapidly than expected. Another idea is that the first black holes, formed from the deaths of giant primordial stars, may have accelerated the process by stirring and compressing the surrounding gas, igniting furious starbursts. And when those same black holes grew and began to shine as quasars, their energy might have quenched star formation, leaving behind the dormant red remnants we now see. Webb's observations have revealed galaxies that existed just 500 to 700 million years after the Big Bang, containing more than 10 billion solar masses of stars. Such mass so early in cosmic history defies nearly every prediction from computer simulations. If these measurements hold true, our models of structure formation may need to be revised fundamentally. Either the universe formed stars more efficiently than we thought, or we are missing some key aspect of how matter behaves under extreme conditions. Perhaps the first galaxies began assembling even earlier than we can currently detect, hidden behind the veil of cosmic reionization, the period when the first light pierced the hydrogen fog of the early universe. The red monsters are not only scientific puzzles but also aesthetic marvels. Their crimson light has travelled for more than 13 billion years to reach us, carrying with it the story of the universe's first great civilizations of stars. When Webb's infrared mirrors captured that light, it was as if we were peering into an ancient city long buried beneath time, suddenly illuminated once more. Each of these galaxies represents a moment when the universe was less than 5% of its current age, yet already filled with order, structure, and complexity. They are reminders that the cosmos wastes no time in its pursuit of grandeur. These early giants may also hold the keys to understanding the evolution of today's massive elliptical galaxies. The red monsters could be their ancestors, once compact fiery systems that expanded and evolved through mergers, growing into the vast, diffuse ellipticals we see in the modern universe. If so, then the same processes that shaped the early cosmos still echo in the galaxies around us today. To gaze upon these ancient red beacons is to glimpse the universe at its most paradoxical young yet old, chaotic yet mature. They reveal that creation does not always proceed in gradual steps. Sometimes it leaps ahead, forging giants in the cradle of time. The red monsters remind us that even at the very beginning, the universe was capable of breathtaking complexity and speed. In their deep crimson glow lies a message from the dawn of existence, that the cosmos from its first moments has been both restless and magnificent, forever racing ahead of our understanding. Before galaxies, before clusters, before the universe as we know it took shape, there was only darkness. For nearly 400 million years after the Big Bang, the cosmos lay shrouded in a fog of neutral hydrogen, opaque to visible light. The first stars had not yet ignited. There were no suns to illuminate the void. This era, known as the Cosmic Dark Ages, was a time of stillness and potential, a universe waiting for its first spark. Then, from the depths of this cosmic silence, light was born. The first generation of stars population 3, stars blazed into existence, immense and short-lived, composed almost entirely of hydrogen and helium, the only elements the universe had yet forged. These primordial giants were unlike anything that came after. Many were hundreds of times more massive than our Sun, their cores burning at unimaginable temperatures. They lived fast and died violently, collapsing into black holes or exploding in titanic supernovae that scattered the first heavy elements, carbon, oxygen, iron, into the surrounding space. With their brief lives, they transformed the universe forever, ending the darkness and beginning what astronomers call the cosmic dawn. The light from these first stars began to ionize the hydrogen gas around them, gradually turning the opaque fog transparent. This process, known as ionization, marked one of the most dramatic transitions in cosmic history. Over hundreds of millions of years, as more stars and the first galaxies formed, their radiation carved out expanding bubbles of clear space that eventually merged, allowing light to travel freely across the cosmos. The universe became luminous, structured, and visible for the first time. These earlier stars also gave birth to the first galaxies, small, irregular gatherings of a few million stars bound together by gravity. They were chaotic and primitive, yet within them lay the seeds of everything that would follow. Through collisions and mergers, these small proto-galaxies combined to form larger systems, setting the stage for the grand spirals and ellipticals of later epochs. Every galaxy we see today, including our own Milky Way, can trace its lineage back to those first flickering lights that broke the darkness. Observing this era directly is one of astronomy's greatest challenges. The light from the first stars has travelled for more than 13 billion years, stretched into infrared wavelengths by the expansion of the universe. Only instruments like the James Webb Space Telescope with its powerful infrared vision are capable of detecting this ancient glow. Already, Webb has glimpsed galaxies existing just a few hundred million years after the Big Bang, some so bright and massive that they defy explanation. These detections hint that the first stars may have formed even earlier than we thought, perhaps as soon as 100 million years after time began. The cosmic dawn was not just the birth of light, but the origin of complexity. Before the first stars, the universe was a simple sea of gas, smooth and uniform apart from tiny fluctuations in density. But gravity amplified those fluctuations, gathering matter into denser regions where the first stars could ignite. Their radiation and explosions then reshaped their surroundings, triggering new waves of star formation and enriching space with the elements that would one day make planets and life possible. Each generation of stars built upon the last, gradually increasing the universe's chemical diversity and structure. The light from the first stars also carried the first information. It revealed the universe to itself, tracing out the web of dark matter that served as its unseen skeleton. Where dark matter was densest, galaxies formed. Where it was sparse, cosmic voids expanded. Thus, even in those earliest moments, the cosmic web was beginning to take shape, its threads glowing faintly with the first light of creation. To imagine the sky of the cosmic dawn is to picture a universe utterly alien to our own. There were no grand spirals, no majestic clusters, only small flickering beacons in a sea of darkness. Yet those beacons contained the essence of all that was to come. From their ashes emerged the next generations of stars, black holes and galaxies. The first black holes, born from the collapse of the most massive population 3 stars, may have served as seeds for the supermassive black holes that now anchor modern galaxies. In this way, The entire visible universe, the vast tapestry of light and structure, was woven from the brief lives of those first giant suns. When we look into the distant universe today, we are not just observing light, but witnessing the moment creation began to organize itself. Every photon from that era carries a whisper from the beginning, a story of transformation from simplicity to splendor. The cosmic dawn reminds us that light, once born, never truly dies. It travels endlessly through space and time, connecting the present to the past. It is the oldest memory of the universe, the moment when darkness gave way to the first breath of illumination. And though billions of years have passed, that light still reaches us. Faint but eternal, a message from the moment the cosmos first learned how to shine. When two galaxies collide, the result is not destruction but transformation, a slow, magnificent reshaping that unfolds over hundreds of millions of years. Among the most striking examples of this process is the pair known as the Antennae Galaxies, two spiraling giants locked in a gravitational embrace about 60 million light-years away in the constellation Corvus. Named for their long, arching tidal tails that sweep out into space like insect antennae, these galaxies offer a living portrait of what happens when worlds collide on a cosmic scale. The antennae began their dance roughly 500 million years ago, when the two galaxies first passed close enough for their mutual gravity to tug at each other's stars and gas. From that moment on, they became entwined, drawn together by invisible threads of force. Over time, their once orderly spiral arms were torn apart, flung into immense arcs that now stretch for hundreds of thousands of light-years. Within these tails, stars are scattered like sparks, drifting into intergalactic space, some destined never to return. Yet amid this chaos, creation flourishes. The collision has compressed vast clouds of gas and dust, triggering an extraordinary burst of star formation that makes the antennae one of the most active star-forming regions in the nearby universe. Infrared and ultraviolet images reveal hundreds of brilliant clusters where tens of thousands of new stars are being born. These clusters are the precursors of future globular clusters, the dense stellar swarms that orbit mature galaxies like jewels. The antennae's core glows intensely, a maelstrom of stellar nurseries, supernovae, and glowing hydrogen clouds. To the human eye, if we could see it in visible detail, it would resemble a cosmic storm, beautiful, violent, and alive with energy. The forces shaping the antennae are the same that will one day reshape our own galaxy when it merges with Andromeda. The two parent galaxies are still distinct but no longer separate. Their centers orbit each other while slowly spiraling inward, drawn together by gravitational friction. In another few 100 million years, they will coalesce into a single, more massive elliptical galaxy. By then, the tidal tails will fade, their stars dispersed across the halo, and the central regions will settle into a new equilibrium, luminous but serene. For astronomers, the antennae offer a window into every stage of galactic evolution, from the first encounter to the final merger. Observations from the Hubble Space Telescope and the Atacama Large Millimeter Array have revealed that the collision has compressed molecular gas into dense knots thousands of light-years across. Within these knots, stars form at rates hundreds of times faster than in normal galaxies. Yet even as new life is born, old stars die spectacular deaths. Supernova explosions scatter heavy elements, carbon, oxygen, iron enriching the interstellar medium with the building blocks of future worlds. Each explosion also sends shockwaves that can both trigger and extinguish further star formation, creating a delicate balance between birth and destruction. The antennae are a microcosm of cosmic evolution, a self-regulating ecosystem of gravity and energy where destruction begets creation. Their long curved tails are more than aesthetic features, they are records of motion, tracing the paths of stars pulled out by tidal forces. Each arc tells a story of gravitational struggle, of orbits twisted and stretched across light years. In time, these tails will dissolve into the surrounding space, their stars joining the diffuse halo of the merged galaxy, faint remnants of the collision that created them. What makes the antennae particularly fascinating is their temporal significance. In the vast chronology of the universe, galactic mergers are not rare, but catching one in this exact phase, a midway point where both galaxies are still recognizable, yet already deeply intertwined, is exceedingly uncommon. It is like witnessing adolescence on a cosmic scale, the moment of transformation between two identities into one. These collisions are also engines of change for the universe as a whole. Without them, galaxies would stagnate, their gas unperturbed, their stars aging without renewal. Mergers redistribute material, reignite star formation, and feed central black holes, sometimes creating quasars that outshine entire galaxies. Every great elliptical galaxy, serene and smooth today, was once the site of such a spectacular union. Thus, the antennae are not just two galaxies colliding, they are an illustration of the process that built the cosmos. When future astronomers observe the Milky Way and Andromeda, in their merging phase billions of years from now, they will likely see a scene much like this: a bright, distorted core surrounded by swirling tails of light, a galaxy remaking itself in fire and gravity. The antennae remind us that in the universe, creation and destruction are one and the same act, different faces of the same eternal motion. Their entwined arms stretch outward like hands reaching across the abyss, frozen in a moment of graceful violence that defines the rhythm of cosmic evolution. To gaze upon them is to see the universe at work endlessly reshaping itself, turning chaos into form and ensuring that even in collision there is always beauty. In the vast expanses of the universe, galaxies rarely travel alone. They gather in immense families clusters containing hundreds or even thousands of members, bound together by gravity and embedded in oceans of dark matter. These colossal congregations, some stretching tens of millions of light-years across, are among the largest structures held together in the cosmos. But inside these crowded environments, galaxies live dangerous lives. They are constantly pulled, stripped, and reshaped by the invisible forces that dominate their surroundings. Clusters are not serene gatherings. They are cosmic battlefields where galaxies wage silent wars for survival. One of the most studied of these is the Coma Cluster, a massive collection of over 1,000 galaxies located more than 300 million light-years away. Through telescopes, it appears as a dense swarm of faint smudges scattered across the sky. Yet each smudge is a galaxy containing billions of stars. Within this cluster, galaxies move at extraordinary speeds, up to 1,000 kilometers per second, careening through a medium of hot, thin gas known as the intracluster medium. This gas, heated to tens of millions of degrees, glows brightly in X-rays and fills the space between galaxies like an invisible tide. When a galaxy plunges into it, the pressure of this medium acts like a cosmic wind, stripping away its gas and halting the formation of new stars. Over time, the once blue spiral galaxies of the outskirts fade into red, quiescent ellipticals near the core. This transformation is known as galactic harassment, a term that captures both the violence and the subtlety of the process. As galaxies tumble through the cluster's gravitational field, they experience tidal forces that distort their shapes and fling out streams of stars. Smaller galaxies are shredded completely, their material recycled into the cluster's diffuse halo. Even the larger ones are scarred, their delicate disks warped, and their gas reserves depleted. The Coma Cluster, once filled with star-forming spirals, now glows primarily with the light of old stars, a silent graveyard of cosmic evolution. Yet this destruction is also a form of renewal. The stripped gas mixes into the intracluster medium, enriching it with heavy elements from generations of dead stars. When clusters eventually merge with others, this enriched material becomes the seedbed for new bursts of star formation elsewhere in the universe. The process is both cyclical and eternal, a grand recycling mechanism that ensures nothing in the cosmos is ever truly lost. Other clusters tell similar stories. The Virgo cluster, our nearest large neighbour, shows galaxies caught in various stages of this transformation. Some still cling to their gas and form new stars, while others are ghostly remnants of what they once were. The cluster's central giant, M87, dominates the region with its enormous halo and the supermassive black hole at its core, one of the first ever imaged directly. Around it, hundreds of smaller galaxies orbit like moths around a flame, gradually falling inward to be consumed. In such dense environments, collisions are frequent. Unlike the slow, graceful merger of the Milky Way and Andromeda, cluster collisions are chaotic, multi-body events. When two clusters collide, the energy released is colossal, the most powerful known since the Big Bang. The galaxies themselves mostly pass through one another unharmed, but their dark matter halos and hot gas clouds interact violently, creating shock waves that ripple through space for millions of light years. One of the most famous examples is the Bullet cluster, where a smaller cluster has punched through a larger one, leaving a distinct separation between its dark matter and gas. This separation, revealed by gravitational lensing, provides some of the strongest evidence that dark matter is real and distinct from normal matter. Clusters under siege are laboratories of cosmic evolution. Within them, we witness every phase of galactic life, from birth to death to rebirth. They show how environment dictates destiny. A galaxy born in isolation can thrive and build spiral arms, while one born in a cluster is likely to be stripped, compressed, and transformed into a featureless elliptical. Over billions of years, clusters evolve from chaotic gatherings into smooth, massive conglomerates of aging stars, surrounded by faint halos of hot gas and dark matter. Yet even then, their stories are not over. Clusters themselves are drawn together by the same gravitational forces that bind galaxies. They too merge, forming superclusters and eventually feeding into the vast cosmic web that spans the universe. In this sense, a cluster is both a microcosm and a bridge, a snapshot of galactic life within a larger unfolding order. To observe them is to see the universe's most fundamental drama played out in grand scale. The struggle between gravity and expansion, creation and dissolution, individuality and unity. The galaxies within these immense structures may seem like victims of their environment, but in truth, they are participants in a deeper rhythm. Their destruction enriches the cosmos, their collisions light up the dark, and their deaths give rise to new beginnings. Clusters under siege remind us that even in the most violent corners of the universe, every act of loss serves the greater architecture of creation. Beneath the glittering expanse of galaxies lies an invisible architecture that holds the cosmos together. It is not made of stars or gas or anything that emits light. Instead, it is composed of something mysterious and unseen: dark matter, the cosmic scaffolding upon which the visible universe is built. Though it cannot be observed directly, its presence is revealed through gravity, bending light, shaping galaxies, and forming a vast interconnecting network known as the cosmic web. This immense structure, stretching across billions of light years, is the hidden framework of existence, a web of shadow binding everything we can see into a coherent whole. The discovery of dark matter's influence began with the work of astronomers who noticed that galaxies rotated far too quickly to be held together by the gravity of their visible stars alone. Something unseen must be adding mass, preventing those galaxies from flying apart. Over time, it became clear that this mysterious substance outweighs ordinary matter by a ratio of about 5-1. Yet its nature remains elusive. It does not emit, absorb, or reflect light. It interacts with the universe only through gravity, and perhaps through subtle forces still beyond our detection. To visualize it, cosmologists run vast computer simulations that track the formation of structure in the early universe. Starting from the nearly uniform conditions of the Big Bang, these simulations allow matter to clump under gravity, revealing a filigree of filaments and nodes patterns that mirror the large-scale distribution of galaxies we observe today. Within those filaments, galaxies form like dew along the strands of a cosmic spider's web. The densest knots become galaxy clusters, the glowing hubs of the network, while the spaces between them expand into enormous voids, almost empty of matter. This invisible lattice is what shapes the grand design of the cosmos. The term dark web of the universe captures both its mystery and its function. It is the hidden infrastructure that connects all things, guiding the formation of galaxies and the flow of cosmic evolution. Without it, the universe would be unrecognizably different. Structure would never have coalesced, stars might never have formed, and life itself would have remained an impossibility. We owe our existence to a substance we cannot see or touch, a reminder of how much of reality lies beyond our senses. Astronomers map the dark web through a phenomenon called gravitational lensing, where the gravity of invisible matter bends and distorts the light from distant galaxies. By analyzing these distortions, scientists can infer the distribution of dark matter, tracing its ghostly outlines across space. The resulting maps reveal filaments stretching for hundreds of millions of light years, connecting clusters like highways between cities. In these maps, luminous galaxies appear as bright intersections within a vast and shadowy network. The beauty of this hidden geometry lies not only in its scale, but in its consistency. From the tiniest galaxies to the grandest clusters, the same web-like pattern repeats, an echo of the initial fluctuations in the early universe. The origin of this cosmic web lies in the smallest imperfections of the Big Bang minute differences in density that gravity amplified over billions of years. Dark matter, being immune to radiation pressure, began clumping early, providing the gravitational wells into which normal matter could fall once the universe cooled. In a sense, dark matter was the universe's first architect, sketching the outlines of structure long before light ever touched it. Yet even now, we don't know what dark matter truly is. Theories abound. Perhaps it consists of weakly interacting massive particles or WIMPs that rarely collide with ordinary atoms, or maybe it is made of axions, hypothetical particles that whisper faintly through the fabric of space. Some physicists propose even more exotic possibilities, that dark matter could be primordial black holes, relics of the universe's first seconds. Despite decades of searching, experiments deep underground and in space have yet to detect a single dark matter particle. Its elusiveness only deepens the mystery, and yet its influence is everywhere. The shape of galaxies, the motion of clusters, even the pattern of the cosmic microwave background all bear its signature. If we could see dark matter, the universe would appear as a delicate, glowing mesh surrounding every galaxy, binding them into a grand design of almost organic complexity. The dark web is the universe's unseen soul, the invisible hand guiding creation. It connects every star and planet to an ancient order written in gravity's script. To study it is to confront the limits of human perception, to admit that what we see is only the surface of reality. Beneath that surface lies a cosmos far richer and stranger than light alone can reveal, a vast web of darkness that holds the shining universe in its grasp. Among the billions of galaxies that fill the universe, most glow with the light of countless stars, their shapes and colours painting the cosmos with familiar brilliance. Yet there exists another kind of galaxy one that hides almost completely from sight. These are the invisible galaxies, systems so dim and diffuse that they evade even the most sensitive telescopes. Some emit only the faintest traces of light. Others seem to contain no stars at all. They are the ghosts of the universe, drifting silently through the cosmic web, detectable only by their gravitational influence. Their discovery has reshaped our understanding of what a galaxy can be. For decades, astronomers assumed that every galaxy must contain both stars and dark matter in roughly predictable proportions. Then came the ultra-diffuse galaxy's enormous systems as wide as the Milky Way, but with only 1,000th of its stars. These vast, faint clouds challenge every expectation. They appear almost transparent, their starlight so weak that it blends into the background of space. Some are visible only through long exposure images that reveal ghostly smudges barely distinguishable from noise. The question that haunts astronomers is simple. How can something so large be so empty? The answer lies in the complex relationship between gravity, gas, and dark matter. In normal galaxies, dark matter forms a dense halo that pulls in gas, allowing it to cool and form stars. But in these ultra-diffuse galaxies, that process seems to have been disrupted. Some may have formed in environments where supernova explosions or cosmic winds blew away their gas before it could condense. Others may have been torn apart by tidal forces, their stars scattered, their dark matter halos stretched thin. Whatever their origin, these dim giants stand as reminders that the cosmos is full of unfinished creations, galaxies that never reach their potential. More mysterious still are the so-called dark galaxies, systems that appear to contain vast quantities of gas and dark matter, but almost no stars at all. Their existence was long suspected but difficult to prove. In a few rare cases, astronomers have detected clouds of hydrogen, moving as if held together by an unseen mass, yet showing no trace of starlight. One example, known as Virgo High 21, resides in the Virgo cluster. Radio observations reveal a massive cloud of hydrogen, rotating as if around a gravitational center, but when optical telescopes search for stars they find nothing. It is as though we are witnessing a galaxy that began to form but somehow failed to ignite. These dark galaxies may represent a missing link in cosmic evolution prototypes that never crossed the threshold into luminosity. Some theories suggest they are victims of cosmic reionization, the era when the first stars flooded the universe with radiation, strong enough to strip gas from small halos, preventing further star formation. Others propose that dark galaxies are simply ordinary galaxies that lost their gas in violent encounters, leaving behind invisible skeletons of dark matter. Their existence has profound implications for our understanding of the universe's hidden mass. If dark galaxies are common, they could help explain discrepancies between the number of visible galaxies and the number predicted by simulations. In essence, the universe might be filled with invisible worlds, unseen but gravitationally real, shaping the cosmos from the shadows. Detecting them requires ingenuity. Astronomers rely on indirect clues, subtle distortions in the motion of nearby galaxies, the bending of light through gravitational lensing, or faint radio emissions from cold hydrogen gas. Instruments like the Arecibo Observatory and the upcoming Square Kilometre Array are expanding our ability to listen to the whispers of these dark systems. Through these observations, we're beginning to map the unseen architecture of the cosmic web in unprecedented detail. The study of invisible galaxies is not merely a technical challenge, but a philosophical one. It forces us to confront the limits of perception and to acknowledge how much of reality lies beyond sight. For every bright, star-filled spiral that captures our imagination, there may be dozens of hidden galaxies drifting unseen. Together, they form the silent majority of the cosmos worlds that exist without light, shaping the universe in obscurity. Some astronomers even speculate that our own Milky Way may be surrounded by dozens of these invisible companions, faint halos of dark matter and diffuse gas that orbit unnoticed. If so, the sky above us may be far more crowded than we realize. The invisible galaxies remind us that darkness is not the absence of being, but a different mode of existence. They show that the universe is not defined by what shines, but by what holds the shining things together. Beneath the glitter of the night sky lies an unseen cosmos, vast and alive, where light is the exception and shadow the rule. As we ascend the cosmic ladder from galaxies to clusters and beyond, we begin to glimpse the true scale of the universe's architecture. What appears at first to be a random scattering of galaxies reveals, when mapped in 3 dimensions, a magnificent and intricate pattern, one of filaments, walls, and immense voids stretching across billions of light-years. These structures, known as superclusters and great walls, are the largest coherent entities ever observed. They represent the skeleton of the universe on its grandest scale, where galaxies are but atoms in a vast cosmic body. Our own home, the Milky Way, belongs to one such formation, the Laniakea supercluster. Spanning over 500 million light-years and containing more than 100,000 galaxies, Laniakea's name meaning immense heaven in Hawaiian captures both its enormity and its beauty. It is not a cluster in the traditional sense, but a vast gravitational basin, a region where the flow of galaxies converges toward a central attractor. Every galaxy within its boundaries, including our own, moves along invisible currents shaped by gravity, drawn slowly toward a region near the Centaurus cluster. Laniakea itself is only one section of an even larger tapestry, a single continent within the cosmic ocean. Beyond its borders lies the Shapley supercluster, an even denser concentration of galaxies over 650 million light-years away. And beyond that, the Hercules Corona Borealis Great Wall, a titanic structure extending more than 10 billion light-years, so large that it challenges the very notion of cosmic uniformity. According to the cosmological principle, the universe should appear roughly the same in all directions on the larger scales. Yet these colossal formations seem to strain that principle to its limits, suggesting that the cosmos may be more complex and anisotropic than our theories predict. The existence of such massive structures raises profound questions about how gravity, dark matter, and dark energy interact over time. How could such vast assemblies have formed in only 13.8 billion years? Simulations of large-scale structure formation show that galaxies are not evenly distributed, but cluster along filaments of dark matter that connect to nodes of density like veins in a living organism. Superclusters arise where these filaments intersect, forming regions of enhanced gravity that gather galaxies together over billions of years. In this cosmic web, matter flows like water through channels, collecting in basins of density and leaving behind the vast cosmic voids that make up most of the universe's volume. The great walls are the ridges between these voids, colossal sheets of galaxies that mark the boundaries between emptiness and abundance. To map such structures, astronomers use redshift surveys, measuring how the wavelengths of light from galaxies stretch as the universe expands. Each data point represents not just a position in space, but also a moment in time, a glimpse of the universe as it once was. When plotted together, the galaxies form patterns that look almost biological tendrils and knots that mirror the neural networks of a brain or the roots of a tree. The resemblance is purely metaphorical, yet it evokes a sense of cosmic connectivity that transcends our ordinary understanding of scale. The Sloan Great Wall, discovered in 2003, was the first of these immense structures to astonish scientists, spanning more than 1 billion light-years. For years it was considered the largest known entity in the universe, until surveys revealed even grander formations. The discovery of the Hercules Corona Borealis Great Wall in 2013 stunned astronomers with its scale 10 billion light-years across, encompassing light that began its journey when the universe was less than 1/3 of its current age. Its existence may point to regions of the cosmos where the early density fluctuations were larger than average, or where dark matter behaved in unexpected ways. Yet, despite their immensity, these structures are fragile on cosmic timescales. Over the next 100 billion years, as dark energy drives the accelerating expansion of the universe, gravity will no longer be able to hold such formations together. The galaxies that make up these superclusters and walls will drift apart, vanishing beyond one another's horizons. The cosmic web itself will gradually unravel, leaving behind isolated islands of light adrift in an ever-expanding void. To study the superclusters and great walls is to see the universe at its most majestic and its most transient. They are monuments to gravity's patient artistry, vast luminous cities of galaxies suspended in darkness, and yet they are also reminders of impermanence, destined one day to dissolve into isolation. From our small vantage point, we can chart their outlines, measure their motions, and marvel at their scale, but we can never grasp them as living entities. Their lifespans stretch far beyond the measure of human thought. The Great Walls stand as both evidence and mystery evidence of the laws that shape the cosmos, and mystery in their defiance of simplicity. They reveal a universe that is structured yet restless, immense yet fleeting, a masterpiece still being painted across the canvas of space-time. Between the luminous filaments of galaxies and superclusters lies another kind of cosmic realm, one far more mysterious and haunting. The voids. These vast regions of space spanning hundreds of millions of light-years are almost completely empty. They contain few galaxies, little gas, and almost no visible matter, great dark hollows that make up the majority of the universe's volume. If the cosmic web is the structure of existence, then the voids are its breath, the spaces between the threads, giving the universe its form. To look into a void is to gaze into the deepest silence imaginable, a silence so profound it defies comprehension. The largest of these regions, the Bhuta's Void, is sometimes called the Great Nothing. It stretches nearly 330 million light-years across and contains only a few dozen galaxies scattered thinly through its expanse. To put that in perspective, if the Milky Way were at its centre, the nearest galaxy would be more than 100 million light-years away, a night sky devoid of constellations, a loneliness beyond imagination. Yet these voids are not entirely empty. They contain thin wisps of gas, the faint glow of background radiation, and the ever-present dark matter that threads invisibly through every corner of the cosmos. The physics that created these vast emptinesses is the same that built the cosmic web. In the early universe, small differences in density caused matter to clump in some regions while expanding away from others. The dense regions became the filaments of galaxies and clusters, while the sparse regions expanded faster, hollowing out into the immense voids we see today. Over billions of years, gravity deepened this contrast, evacuating the voids further as galaxies migrated toward the denser filaments. The result is a universe shaped not just by matter, but by the absence of it. Studying these voids has become a frontier of cosmology, for they hold clues to the nature of dark energy, the mysterious force accelerating the expansion of the universe. Because voids expand faster than dense regions, they amplify the effects of cosmic acceleration, making them natural laboratories for measuring how space itself evolves. By observing how galaxies move along the edges of voids, astronomers can test the strength of gravity and the behavior of dark energy across cosmic time. In this way, the emptiest regions of space may reveal the universe's deepest truths. But the voids also hold another puzzle, the mystery of the missing matter. According to precise measurements of the cosmic microwave background and Big Bang nucleosynthesis, we know exactly how much ordinary matter protons, neutrons, and electrons should exist. Yet when astronomers add up all the stars, gas, and dust in galaxies, they find only about half of that predicted amount. For decades, this discrepancy troubled cosmologists. Where was the rest of the baryonic matter hiding? The answer, it turns out, may lie in the vast invisible spaces between galaxies. In recent years, observations using X-ray and ultraviolet telescopes have detected faint traces of warm-hot, intergalactic gas filling the voids and filaments, known as the warm-hot intergalactic medium, or WIM. This diffuse plasma, heated to millions of degrees, is too thin to emit visible light, but it absorbs specific wavelengths from the light of distant quasars passing through it. By studying these absorption lines, astronomers have begun to locate the missing matter, slowly closing the gap in the cosmic ledger. It seems that much of the universe's ordinary matter was never truly missing. It was simply hiding in plain sight, scattered in the dark spaces between galaxies, waiting for instruments sensitive enough to find it. The discovery of the WIM not only solves a long-standing mystery, but also reinforces the vision of the universe as a seamless continuum of matter and energy, where even emptiness is part of the whole. The voids are not barren wastelands, but integral features of cosmic architecture. Their emptiness defines the shape of the filaments that surround them. Their expansion drives the evolution of the universe itself. Within them, dark matter still exerts its quiet pull, shaping invisible structures that may one day host the birth of new galaxies. The interplay between void and structure, between nothing and something, lies at the heart of cosmology. To map the universe is to trace both presence and absence, to recognize that the spaces between are as essential as the objects themselves. The cosmic voids are the universe's silent partners, their vast hollows balancing the brilliance of galaxies. They remind us that the cosmos is not a solid fabric, but a delicate balance of fullness and emptiness, of light and darkness, woven together in perfect proportion. In the end, it may be the voids, not the galaxies, that tell us the most about the nature of existence. For in their stillness lies the geometry of creation, the space in which all things move, and perhaps the echo of the moment when the universe first expanded into being. The universe is not a static masterpiece, but a living, evolving entity, an ocean of motion where every star, planet, and galaxy drifts in endless procession. From the smallest particle to the largest supercluster, all things are caught in the slow, majestic current of cosmic expansion. The galaxies themselves, once clustered tightly in the early universe, now rush away from one another as space itself stretches. This motion is not an explosion through space, but an expansion of space. There is no center and no edge. Rather, every point recedes from every other. If you could stand anywhere in the universe, the view would be the same distant galaxies all moving outward, their light stretched into the red by the fabric of space unfurling between you and them. This phenomenon, discovered by Edwin Hubble in the 1920s, forever changed our understanding of reality. It revealed a universe not eternal and unchanging, but dynamic and finite, born from an origin in time. For billions of years, this expansion has continued, its pace first slowing under gravity's pull, and then unexpectedly accelerating again. The cause of that acceleration is one of the great mysteries of modern science, a force known as dark energy, a term that conceals more than it reveals. It acts like a pressure inherent to space itself, driving galaxies apart faster and faster as the universe ages. Dark energy now dominates the cosmic balance sheet, accounting for nearly 70% of the universe's total energy density. Though invisible and undetectable in any direct sense, its influence can be measured in the way galaxies drift and clusters thin over time. If it continues to behave as it does today, the future of the cosmos is written in quiet isolation. In the far future, galaxy clusters will drift beyond one another's reach. The Milky Way and Andromeda, long since merged into a single elliptical galaxy, will become an island adrift in an ocean of darkness. Beyond its borders, all other galaxies will recede faster than the speed of light, their radiation stretched until it fades from view. The cosmic horizon will shrink, leaving our descendants, if any remain to gaze upon a sky nearly empty, unaware that countless other galaxies once filled it. This vision of the island universe is not mere speculation. It is the inevitable consequence of cosmic acceleration. The large-scale structure of the universe will freeze, its growth halted by the relentless expansion of space. Gravity will hold together only local systems, galaxies, star clusters, and planetary systems, while everything else drifts beyond reach. Yet even within these small havens, time will not stand still. Stars will age and die, leaving behind white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will cool, fade, and vanish. The night sky will grow darker until only the faint glow of evaporating black holes remains. The universe will become a place of cold simplicity, its vibrant complexity reduced to whispers of radiation and scattered particles. This scenario is known as the heat death, a future where entropy reaches its maximum and no energy gradients remain to power motion or life. But not all cosmologists agree that this is the final word. Some propose that dark energy may not be constant, but could change over time. If it strengthens, the universe could face a more violent end, the so-called Big Rip. In that future, the expansion would accelerate without limit, tearing apart galaxies, stars, planets, and finally atoms themselves. Space would expand faster than the forces holding matter together, and the cosmos would dissolve into pure emptiness. Others imagine a different destiny, the Big Crunch, where dark energy eventually reverses its sign, causing expansion to halt and collapse into a final, fiery implosion. In that moment, all matter would be drawn back into a single point, perhaps giving birth to a new cycle of creation, a reborn universe emerging from the ashes of the old. Between these extremes lies the possibility of eternal equilibrium, where dark energy and gravity balance perfectly, and the universe coasts forever in quiet expansion. Regardless of the outcome, the universe's motion is a reminder of impermanence. Every galaxy we see is both a snapshot of the past and a prophecy of change. The light reaching us from distant systems began its journey billions of years ago, long before Earth even formed. When we look outward, we are not merely observing space but time itself, layered in luminous strata across the sky. To contemplate the fate of the universe is to confront both vastness and intimacy, the knowledge that everything we know is part of a grand story of becoming and passing away. The cosmos is neither cruel nor kind. It simply moves, governed by laws that shape beauty and destruction alike. And yet, within this fleeting order, consciousness has arisen, beings capable of looking up, of wondering, of tracing the motion of galaxies and imagining the end of all things. Perhaps that awareness is the universe's way of seeing itself, the brief moment when the cosmos becomes self-aware before fading again into silence. The fate of the universe, whatever form it takes, will unfold beyond all measure of human time. But as long as we can look to the stars and grasp their meaning, we remain part of its story, ephemeral yet eternal in our curiosity.